Okay, thank you. It's a pleasure to speak here. So I'll be interested in Carnot varieties, considered as monotone symplectic manifolds. And in monotone Lagrangian submanifolds, inside them, I'll be mostly interested in monotone Lagrangian tori. For most of the talk. So, I will be comparing, somehow superficially like Tobias was doing in his talk, open Gromov-Witten theory of X relative to L. That means I'm counting holomorphic disks with boundary on L to a different theory, just closed Gromov-Witten theory of X. Okay, so that means counting certain holomorphic curves inside X. So, and specifically the invariants I'll be interested in are the most basic ones in both settings. In the open Gromov-Witten theory, I will be interested in something called the Landau-Ginzburg potential, which I'll define soon. And in the closed Gromov-Witten side, I will be interested in an invariant called the quantum period of the Carnot. Or quantum period. So both of these invariants are extremely classical, but somehow a connection between them seems to have been unnoticed. So, and the idea for comparison, maybe also let me draw a picture, and then I'll return to like a more detailed idea of proof later, is that if I have a closed curve like that, maybe it satisfies some point constraints, and maybe I can put a point constraint to lie on the Lagrangian submanifold. And then, like Tobias was doing in his talk, I would want to stretch these holomorphic curves around the neighborhood of L, and they will break into things. But unlike in Tobias's talk, some parts of the curve will stay in the neighborhood of the Lagrangian, so they will become holomorphic curves in the cotangent bundle, and there will be some pieces of the curve which live outside. So this piece was Gromov-Witten theory. Then these exterior pieces, they are open Gromov-Witten theory of X relative to L. And suddenly we see here a third player appearing. That's something happening in the cotangent bundle. So this is something happening in the string topology of L. Which will also, in the story I'm going to tell today, this will also be something quite non-trivial and interesting. Okay, so let's now define all the invariants I mentioned. I'll start with the quantum period. So it's a formal power series in one variable, which is a generating function of one pointed Gromov-Witten invariant of X. So here, this guy here is the point class in X. So tau sub d minus 2 means I'm computing a descendant Gromov-Witten invariant of the point. So this is a gravitational descendant. I'll remind that in a second. Now d means that I'm computing this Gromov-Witten invariant using holomorphic spheres of Chern number d. And finally t is the formal variable. Okay, so this is a rational number, tau d minus 2 point sub d, which is by definition equal. So I take the homogeny space of all chain z spheres with one marked point, and then I first take all spheres which pass to a specified point in X, that's still a moduli space of large dimension, of dimension d minus 2. So to make this rigid, I wedge it with the first chain plus of a certain line bundle defined by this moduli space to the power d minus 2. And this line bundle is the tautological line bundle. That's the tangent fiber at a mark point of any curve in my moduli space. Okay, so this becomes a number. So maybe a small remark for, if people are not very comfortable with this kind of descendant operations, you can also see this invariant in a slightly different but more enumerative way. You could just count. So that's also equal 1 over d minus 2 factorial times the following integral count. I'm again counting turn number of these spheres, again passing through a specified point on x, and this problem is rigidified in the following way. I fix a germ of a complex hypersurface sigma defined locally in a neighborhood of this point. So I'm assuming that I'm using an almost complex structure that's integrable in a neighborhood of this point, but otherwise generic, almost complex. Okay, and then I require these curves to have tangency of order d minus 2 at that point to this germ of a hypersurface. So imposing this tangency order condition roughly means like integrating this Chern 1L to the d minus 2 up to this factorial factor. So this equality, like this, it's a rather simple way. Yeah?
So if I would sort of push this SFT perspective and everything, then so that one I could say something about some orbit or something by stretching around the device.
So if it's a globally defined divisor, you can have a high degree divisor, so it doesn't have maybe a whole lot of spheres, then you can stretch, and then it will be just this re-orbit, yes, of multiplicity d minus 2.
And in this string topology, could I also replace it by SFT of unit potential?
Sure. So, I mean, yeah, so if you have this tangency guy, you can stretch it around the hypersurface or around the Lagrangian. I will be doing this around the Lagrangian. I mean, it's
I could replace the string topology by saying something about SFT.
Sure, yeah. But it is string topology.
So we just discussed L equals dimension or L equals 3 before, right?
Yeah. Okay, so that's the closed string geometry invariant. I'll be studying. Let's discuss the open part. Okay, so then I take the Lagrangian submanifold. So first, as I said, I'll differentiate monotone ones. So monotone means that the following two maps. So I take H2X rel L, I can compute areas of these classes, and I can compute their master numbers. So these two maps have to be positively proportional. Okay, so maybe an example is that if I take a product torus in C squared, norm Z1 equals R1 and norm Z2 equals R2, this guy is monotone if and only R1 equals R2. Okay, so because it bounds, this thing is generated by this fiber disk in the first coordinate, fiber disk in the second coordinate. Both of them has mass of index 2 and areas pi r1 squared and pi r2 squared. So those areas must be the same. And another example is if I take the standard toric vibration from CP2 to the moment triangle, the preimages of every point in this triangle is a Lagrangian torus, but only one of them is going to be monotone. That's the torus living over the barycenter of the triangle. Okay, so take a monotone Lagrangian submanifold, fix a normal complex structure, and fix a basis for the first homology of that Lagrangian. Maybe ignoring torsion. So then the Landau-Ginzburg potential of L is a Laurent polynomial, which is a generating function counting holomorphic Maslov index 2 disks with boundary on L. So I'm counting all Maslov 2 disks, passing to a specified point on L that makes them rigid. I could just count there and get a number, but I want to retain more information about them. Specifically, I want to retain the information about their boundary homology classes. So if I denote the boundary homology class by the vector L1.Ln in a chosen basis, I'm just going to associate the corresponding monomial x1 L1.xn Ln, and I sum these monomials over all holomorphic Maslov 2 disks. That's a finite number, so the sum becomes a Laurent polynomial in n formal variables. So let's do examples. The product torus in C squared has potential equal x1 plus x2 because there is a holomorphic disk in the first C factor whose boundary is one basic loop on the torus and another holomorphic disk in the second factor that's a second basic loop. So if I take the standard fiber in CP2 called the Clifford torus, its potential will be x1 plus x2 plus 1 over x1, x2. So there are kind of three families of holomorphic disks like that. And moreover, maybe the last example is if I take a toric Fano variety and L to be the standard monotone toric fiber, so there's kind of some standard Lagrangian torus that sits there. Then by theorem of Cho and O, we know that its potential is equal to like the Horry-Buffer potential, so the standard toric potential, which is precisely this guy for CP2. Any questions? Okay. So recall that we produced a generating function out of Riemann-Wittenberries. Actually, I forgot to call it by name, so I call it G sub x, the quantum period of x. That's the generating function of all these Riemann-Wittenberries. I want to produce the same generating, analogous generating function for the Landau-Ginzburg potential, capturing the following. So let's put, so if W of x1 dot xn is a Laurent polynomial, let's denote by phi d of W the constant term of its deep power. Okay, so for example, phi 3 of x1 plus x2 plus 1 over x1, x2 would be equal to 6. And I put these numbers, these constant terms, together in a generating function called pi sub W, I normalize them by d factorial, and then I put phi d, sorry, of W times t to the t. So this number or this generating function are called the classical period or period of W.
So Dimitri,
Yeah.
on that remark there should be like d factorial perhaps on the bottom.
No, it's actually I think that's d minus 2 factorial.
Because it's not like the d factorial that should go with the power of t to the d over there. To your phone on the quantum period.
So both are correct. Yes, both equalities will be correct. So there is a slight. So when you stretch this kind of, I'll come to it.
Okay.
When you stretch the count will not be 1 or something with the screen.
Does this classical period determine W?
That's a very good question. So I think so. No, because like mutations preserve classical periods. So you could wonder, does it preserve them? Like, does it determine some list of Laurent polynomials that differ by some cluster algebraic structure? And that's like a kind of, a hard problem which is solved for CP2. I'll come to that a bit later. Okay, so the main theorem is that periods theorem, if X is phono and L is a monotone Lagrangian torus, so this is the place where torus is important. Like the general definition of Landau-Ginzburg potential works for all topologies. Then the classical period of the Landau-Ginzburg potential of L is equal to the classical period, to the quantum period of X. Or like comparing term by term, what that means is that, constant term of W to the power D, of the Landau-Ginzburg potential to the power D, is equal to 1 over d factorial times the corresponding Grand-Grid invariant. And that holds for all D. I think that includes the statement that the constant term of W itself has to be found. So, as a corollary, well, we know that, like, for example, toric phonos contain, the standard toric polynomial, but in fact we know that phono varieties contain a lot of different monotone Lagrangian tori. For example, Renato constructed infinitely many monotone Lagrangian tori in Delpetto surfaces. And moreover, we know that kind of the structure of this story is very interesting because it relates to cluster algebra. I will talk about this a bit later. So, but anyway, it's a reasonable question to try to classify monotone Lagrangian tori in a Phono variety. And that's very hard, but as a corollary, we get some information about the enumerative geometry of all Lagrangian tori. We know that the constant terms of the Landau-Ginzburg potentials are all equal to each other. L and L prime are two different monotone Lagrangian tori. Then their potentials have periods which are equal. Okay. So I will discuss kind of this story about CP2, which is very well understood a bit later. Before I do that, let me tell you two pieces of evidence. Looking at which you might have guessed that this statement should hold true. So the first known piece of evidence is that, well, if X is toric and L is the standard monotone Lagrangian torus, the standard toric fiber, then this equality follows from Cho and Zhou that computes WL and Gauss mirror symmetry that computes the quantum period. So in this case, theorem follows from Cho and O plus given so. And second piece of evidence, so as I mentioned very briefly, like for example in CP2 and in maybe in different toric phanos, you can mutate Lagrangian tori and produce new monotone Lagrangian tori, and you can sometimes obtain explicit wall crossing formulas that relate the potentials of those tori, and those wall crossing transformations can be explicitly checked to preserve periods of Laurent polynomials. So in particular, we know that the periods of the potentials of all Viennese tori are the same. So, and then let me elaborate a bit more on this story with wall crossings. By looking at the following very brave conjecture. So, if X is a Fonda variety, so the mirror to a Fonda variety should be a Landau-Ginzburg model, and the way to construct it is as follows. So first we start with X check, which is the mirror to the open Calabi-Yau manifold X minus smooth and economical divisor. So this X check itself will be a complex variety. It should have, moreover, the expectation of mirror symmetry tells me that it should carry a proper map onto C with compact fibers, or if you want like a holomorphic, you should support a holomorphic function W with proper fiber. And because the fibers are proper, this holomorphic function is essentially the unique holomorphic function you could construct on X check up to a constant factor. So now this pair X check comma W, called the Landau-Ginzburg model, is mirrored to X, to the final itself. And there are different versions of mirror symmetry you can state. For example, homological mirror symmetry is telling that the Fukui category of X should be the category of matrix factorizations of X check comma W. But you can also do some other more geometric statements. And here is a different conjecture. So what I could do is I could look at Landau-Ginzburg potentials of all possible monotone Lagrangian tori in X, well, mod SLN Z. Because I need to fix a basis in the first homology of the torus, so the potential is actually defined after that. That is a list of some Laurent polynomials which is usually infinite. For example, for CP2, that's indexed by Markov triples. So maybe I should mention that in a moment. So that's usually some infinite list of Laurent polynomials, and that should be in bijection. So it should be the same list of Laurent polynomials as I could obtain from the mirror by taking W, this Landau-Ginzburg model that lives over X check, and restricting it to various cluster charts that can live in X check. So the cluster chart is just an algebraic embedding of C star to the n into X check. So it's kind of, X check is not expected to be a cluster variety in high dimension, but somehow it should still somehow carry various embeddings of C star to the n in it. And if I restrict W onto that, that's going to be a regular function of C star to the n. So I can write this down as a Laurent polynomial. So kind of these two lists should be the same. And I think this kind of conjecture is a little bit close of like what Coates and collaborators do when they try to classify Fano manifolds. Probably this list of infinite Laurent polynomials should determine the Fano union. What this conjecture does, it kind of throws in this kind of mirror side of the story when, kind of maybe it throws in the Grandjean theorem. Okay, and so now I want to say the following. So basically this conjecture is now known for CP2. So two results. First, the set of all cluster charts in the mirror to CP2 was computed by Prince, at least if you understand the mirror not in the complex way, but in the Gross-Seibert way. So kind of there is an analogous conjecture where instead of X check as a complex mirror, you construct X check as a Gross-Seibert. So cluster charts in CP2 check, all in bijection with Markov triples, which are also known to be in bijection with the anatomy. Okay, and the second thing we know is the result of Akhtar and Kasperczyk telling me that if a Laurent polynomial in two variables has the same period as the standard potential for CP2, x plus y plus 1 over xy, then this potential is one of either potential over the anators. So it's related by a specific set of mutations to this Laurent. So so as a corollary, kind of this brave conjecture holds for CP2, and maybe more concretely, we know that every monotone Lagrangian torus in CP2 has the Landau-Ginzburg potential over the anators. So this combines 2 plus the quantum periods theorem. And in fact, the conjecture is to combine both of these things and quantum periods theorem.
So Dimitri, do
Yeah.
you happen to know, like, if Galkin have already predicted all like these potentials for all the Delphi surface already?
Mm-hmm.
Did they take a look at it to say like same theorem for them? Number 2?
I think number 2 only exists for CP2, if I'm not mistaken.
Can ask more from that.
Yeah, but I should check. So,
I want to know
sorry,
if
so
they,
maybe,
if they
maybe
would
two
just
exist
like,
for every. Sorry, two exist for everyone, even for some singular Zolkowskis. But I think one exists only for sequences.
okay.
But I'm not sure. I should check. Okay, so this was kind of, I was kind of, this corollary is some, a corollary if you're interested in the Lagrangian theorem. But also, one more thing I would like to explain before I proceed to the proof idea is that maybe you should be interested in this theorem, in the quantum periods theorem, even if you don't care about the Lagrangian theorem at all, but only care about Rome-Witten theorem. So applications to Rome-Witten theorem. So the first one is going to be kind of a little bit not sure, maybe naive, but people have discussed these things in literature. So we say that Landau-Ginzburg, we say that a Laurent polynomial W is a weak mirror of a Fano X. Well, if it's classical period, computes the quantum period of X. Okay? And this is kind of, and the question people ask when they think about this kind of problems is that does every Fano variety have a Laurent polynomial which is its weak mirror? And because classifying Fano varieties is very hard, answering this question is also very hard. The partial answer in light of this result is that if a Fano has a molten Lagrangian torus, then yes. Okay, because the Landau-Ginzburg potential of that torus will be a very weak mirror. That's the statement of the theorem. So, and another application is that actually maybe I should give a. So the other application is to quantum Lefschetz theorem. But maybe I should first give a proof idea because the quantum Lefschetz will go better after that. So I'll hope to return to that later. Okay, so maybe good. So let us discuss the proof idea. Are there any questions before I do? Yeah?
So then you have many weak mirrors.
Absolutely, yes. Because as many as this, well, probably again as many as this infinite list of Laurent polynomials that are avatars of the mirror Landau-Ginzburg model on various charts. So maybe as many weak mirrors as there are charts in the mirror variety.
Are there any Fanos that we know don't contain Lagrangian torus?
No, we suspect that if a Fano admits a toric degeneration, it should contain a molten Lagrangian torus, and we don't know Fanos that don't. Any other questions? Okay, so the proof idea is to start with this closed column of the curves of chain number D that pass to a specified point and satisfy either this tangency condition or carry that descendant insertion. They compute this Rome-Witten. Okay. So the idea is to put the point constraint inside the Lagrangian in question, the Lagrangian torus. Okay, so I'm drawing the Lagrangian, or maybe like the one. And then I stretch around L, just like Tobias was doing in Stoke. So in general, spheres will break into holomorphic buildings. Which in general may be complicated, but there will certainly be some, recall I have this mark point where I had this tangency condition, all the gravitational insertion. There will certainly be a piece of the curve in the building that inherits the same condition. So, and these parts of the curve live in C star L, and the outer parts live in X minus L. Okay? So, first, using that L as a torus, or precisely the fact that the fluid complex of T star L lives in non-negative degrees, by an index computation, one shows that this part of the curve star, must have at least d punctures. And second, using monotonicity, one shows that they are at most d pieces on the outside, because each of them will be like mass of 2 or higher, and together they must each up to a number precisely d. There are at most d disks, curves, outside. And combining these two facts, one concludes that the only combinatorial way this broken curve can look like is the following. So it's d pieces, all of which are holomorphic planes, and they have mass of index 2. Which are outside, and they're joined together by a single curve with d punctures sitting in T star L, which inherits this tangency condition, which was marked by star. So this argument, like these 2 points, this is an argument of Chidi-Balkin model. So, good. So now let's look at these holomorphic curves. So this exterior piece is the L bijection with holomorphic mass of index 2 disks. So a d tuple of disks would precisely contribute. So a d tuple of disks whose boundary homology class is sum to 0 is precisely what computes phi d phi d of WL. Okay, the constant term of W to the power d will be precisely computed by those people. But now what about these kind of star guys? I need to compute them now. So let me first tell you the statement and then the way to compute. So now you see so now I have obtained a connection for between closed Gromwitten theory and open Gromwitten theory, but via an unknown term which lives in string topology, so I will be discussing this kind of unknown thing in string topology. I call this operation a gravitational descendant operation, so I call them descendants, because they have this insertion. Okay, so theorem that descendants in T star Cn give a well-defined operation, or give well-defined operations which eat up like d inputs, where d could be arbitrary. And they go from sh0 of t star tm tensor d. So each input lives in syntactic homology of degree 0, which is itself a Laurent polynomial ring. So I'm taking kind of d tuples of Laurent polynomials or like Laurent monomials, and that goes to z. So I just count the number of curves. Okay, so I have well-defined operations, and now the statement is that we can compute them. So the computation is that for any d tuple of vectors in z to the n, which it holds that so a vector in Zn gives me a kind of a Laurent monomial written as x to the power v1, and then x to the power vd. So that should be a number, one of my descendants. And the claim is this is equal to d minus 2 factorial if the vector is sum to 0 and 0 otherwise.
What is the fancy x?
So fancy x is it's x1 to the power v1, its first coordinate, dot xn v1 nth coordinate. It's monomial. Which represents like a homology class of this input orbit. You can also see v1 as an element of the first homology. Okay, so so yes, if you kind of match this computation with the gluing construction, you prove the quantum period theorem. So how do we prove this? How do we compute these descendants? So, for this it's very helpful to somehow broaden the perspective and notice that generally, if M is a Liouville domain, like a cotangent bundle of a manifold, the Fourier complex of M is an L-infinity algebra. Okay, so it has structure maps LK from CFM tensor K to CFM, which roughly compute curves like that, with like asymptotic markers. And if you look at like generations of this modulus petity for dimension 1, you just get two-level buildings like that, which gives you the L-infinity relations. They look like this. They look like K-infinity relations, but you symmetrize them. Sorry, I won't write this through. But unless you want. Okay, and if I look at my curves with the tangency condition, also inside also inside my Liouville domain, so they maybe have, I don't know, maybe k inputs, and this tangency condition at some point to some German hypersurface of order d minus 2. That these guys give me operations which I denote tau kd, from CFM tensor k just to integers or numbers, so they're going to have degree 2 minus 2k if I consider this vector space as being shifted with degree 2d. So these guys would have actually degree 3 minus 2k. Okay, so what I'm hinting at is that theorem, these operations give me, for each fixed d, the connections of these operations where k varies gives me an L infinity augmentation of the L infinity algebra. So fixed d, then these guys, in at least one, is an L infinity augmentation of the floor L infinity structure. Okay. This means that they satisfy analogous equations like this, but I replace the outer guy by tau. So they satisfy quadratic equations like that. Okay, and the proof basically goes by what are the one-dimensional boundary of this modular space is where it looks like this.
Some equals 0, right?
Yeah, thank you. Yeah. So this holds for like all little domains, in particular cotangent bundles of all manifolds. And if you recall that the cotangent, like the L infinity structure on a cotangent bundle of a smooth manifold is conjecturally the Chas-Sullivan L infinity structure in the loop space, you find out that somehow these descendant operations give you some new string topology operations, which have not probably been discussed in the literature. They're all inclusions. The Chas-Sullivan algebra. So to compute descendants for the torus, so two things to note is that first, these chain level operations, which are in general descendants, they, in this particular case, descend in cohomology. Descend in cohomology, that's one. And second is that for the n torus, the L infinity structure has only L2. The only relevant piece which will know somehow, we know the L2, let's do this. We know L2 for the torus. So then we get some relations, like these expressions give me some relations for descendants that allow me to eventually compute them, although that computation is not entirely trivial. But the answer is quite simple, as I said. Okay, maybe I'll take a couple more minutes to tell you about the quantum lattice formula. So maybe, so the upshot, like how the proof went was, I took spheres, like computing descendant invariant, I stretched them around the Lagrangian and broke them in pieces of disks. So broke them into disks. Okay. I could have used any Lagrangian tools to do that. So it turns out that this breaking of spheres into disks is very useful, to study somehow, dimensional reduction of Witten variance. So, in particular for quantum lattice theorem. So that's a theorem due to Coates and Giventhal. Basically, it tells me that if y and x are Fano, y is a smooth hypersurface, and also minus kx minus y is ample. This is kind of the setting of the classical lattice theorem. So it tells me that this last condition tells me that x minus y is Weinstein. So then quantum Lefschetz gives me a connection between quantum periods of x and quantum periods of y by a more or less explicit formula. So now suppose I have some Lagrangian torus in y. Well, ideally it would be monotone, but if I impose some stabilizing divisors condition, then I can kind of, I can run out all my arguments as if I was monotone, although I'm not. So let's not care about monotone too much. So I take a Lagrangian torus called L, and then in the normal bundle to y, I can lift it to a torus one dimension higher in X, called L2. Just circles of like maybe even small radius if I don't care about multis. I can compute potential of L inside y, and so now the point is that there is an explicit formula which is in my joint work with Luis Diogo, Renato Viana, and Wei Wei Wu, which relates the potential of L and y and the potential of its lift inside X. And now, if you understand what this, it's easy to understand what these formulas mean in terms of periods, and we'll find out they precisely recover the quantum Lefschetz formula. Maybe I should draw a picture for how this argument goes. So,
You want to say like we are using wide also and not open.
well, we don't.
We talk later.
So, like, the original proof of quantum Lefschetz kind of uses localization, so it's not really geometric. But here we'll be able to see quantum Lefschetz arising very explicitly. So, start with a holomorphic sphere inside Y, computing the complete period, and then we use this stretching to break it into a bunch of disks with boundary on L. And now, inside the normal bundle, it's very easy to lift holomorphic disks, two holomorphic disks, inside with boundary on L twiddle. But the boundary of these disks, obtained from breaking the sphere, they sum to 0, right? Because they glue back to the sphere. Once I lift the disks in the normal bundle, because it has some curvature, like because this normal bundle is non-trivial, the boundaries of those disks won't sum to 0. They will sum to the fiber class. But also twiddle bound some extra holomorphic mass of two disks precisely in the fiber class. They are these fiber disks. And also, in the case minimal Chern number of the hypersurface is 1, there could also be some extra disks looking like that. So if I reglue them in all possible ways to correct the boundary homologies of these lifted disks and make them 0 again, I can reglue again by this quantum periods theorem any such tuple of disks back to a holomorphic sphere in X. So that's basically how this geometric interpretation of quantum Lefschetz works. So like because you're gluing some mass of two disks which are extra, you could have started with like Chern B spheres and end up with Chern B plus R spheres where R was something like C1 and C1 of X over C1 of Y, C1 of T1 or something like that. So the identities you're getting are not very trivial, but they precisely match the computation of field sentiment. So I guess that's a good time to stop.
Any questions? Comments?
Did you try and compute these descendants operations for anything except the theorem?
No. That would be a very interesting question. So, also, one thing I did not try to compute is that, so suppose that kind of I take a Lagrangian sphere. It doesn't have a superpotential at all, because it only has M0. It doesn't have first homology. So if I stretch like descendants around the sphere, now there are two possibilities, and I don't know which one holds. It's either the string topology of the sphere and the non-trivial unbounded structure in it, plus some open Grom-ring invariance, will still determine also periods. So somehow, but the problem is that when you stretch, you have to understand the components rates of the broken buildings. So what I said can like if you have a chain 6 here, you can break into like Maslov 4, Maslov 2, and something in the string topology. So somehow we capture like not Maslov 2 disks, but some higher Maslov disks. But also I haven't checked whether that happens or not. You can get like more ugly buildings which involve bananas. In that case, like like it's just like what's the components rates behind all this components.
Okay, if there's no further questions, let's thank Dimitri again.